and welcome to this periodic table day celebration for English medium schools. As you guys know that the periodic table day has been constantly being celebrated in other parts of the world, particularly the US, since long, maybe for the last 1 decade. They are observing on every February 7th. February 7th, because on that day, on that particular day, John Newlands presented the first periodic table based on his law of octaves. Although today is the birthday of the father of periodic classification, father of periodic table is not Newlands, is not John Newlands, it is Dmitri Mendeleev. Today is the birthday of the father of periodic table, Mendeleev. We have kept today's date for the continuation of the periodic table day celebration, as we thought that in one day we cannot cover both in Odia medium and in English. And today, whatever we will be discussing will be in English, so that not only the guys who are studying in English medium schools in India can benefit, but also who are from other countries, other places, other native English speaking countries like US, UK, Australia, South Africa, they are the native English speaking countries. They can also take the benefit of this program. First, before we start, let me tell you, I am S.S. Tripathy, the head of a non-government organization, NGO called the Uranium. The term uranium is there, the Uranium, which has been working for the advancement of chemical science among youth in high school level, particularly in the high school level 8, 9, 10, 11, 12. For the last maybe 23, 24 years. Welcome once again, Anisa, Sarthak, Sibdat. Once again, you are repeating. No problem. I will be getting an encouragement for this live session, which is, in an odd time where many of the children are in their schools. I thought possibly by 1 p.m. the schools will be over on Saturdays, but I was told later that even on Saturdays, the schools, particularly the English medium schools, are over after 3:30. So many of the guys will be watching after their school is over. Now, let me tell you, this is the celebration. I'm wearing a t-shirt which has been printed with periodic table, and you guys will be given a prize of periodic table mug, a coffee mug in which beautifully the periodic table has been printed. That is sublimation printing. The cup will break down, but the printing will never ever go. No, I'm not in California. I'm very much in my own home city, Cuttack, Anil sir. I was there in California, but I had returned from US, from California, from San Diego since 2 months. I mean, November 21st, we came here, came back. Now, we will be also, we have already released that song, the periodic table song for 118 elements. We have composed, and it has been professionally designed by audio engineers in professional studios, and that has been video animated by professional houses, and you will be listening to that. And I strongly feel that even if you are a class 9 student, forget if you are 10, 11, 12, if you are a class 9 student, even 8 student, you can be able to draw the periodic table with me while I will be chanting, singing in a particular melody. You will be able to write all the elements. Now, why? Let me tell you why. Before that, let me share my screen. If I share my screen, this is Zoom, and I will be reduced to a minuscule. You can't see me in this uh, big frame. I will be reduced to a very, very small frame, but that doesn't matter. We'll be doing that. Now, when I was at US in my elder son's house, the elder daughter of my elder son, who is my eldest granddaughter, Myra, was who was reading at 7 at that time. Now she will be in 8. She gave me a song from a very renowned organization of science in USA called ASAP. ASAP, ASAP Science. And I heard that song, that is a periodic table song. It was very nice, and it was completely a copy of a popular music called Can Can. And in 2.5 minutes, all the 118 elements have been spelled out in that melody. I thought this won't be of any good use for Indian students, particularly non-native English speaking countries like India and many other countries. Therefore, I decided to produce a similar type of song, periodic table song, but believe me, we have kept nothing in common with respect to that ASAP song. You can just Google search ASAP periodic table song. You hear that, you watch that, and you will be watching now the periodic table song that our trust, our organization, the Uranium, has published. You'll find nothing common between them. We have done with a little bit of Indian melody. They have done completely Western melody. But you know, Newlands was an Englishman, John Newlands. He was a lover of music, and he was influenced by Pythagoras, the Pythagoras theorem that you use for finding out the hypotenuse if the base and height is given for a right angle triangle. A square plus b square is equal to c square. So that the famous scientist Pythagoras, 100 years before, this is 1700 something, I'll give you the story. But before 100 years, he was speaking in terms of music. He was saying every planet, every star is musical. He was saying that I am listening to the vibration, the music that is being sent by different planets. Their frequencies are different, they resonate differently. So, that musical theory of Pythagoras impressed Newlands the most. And by his time, only 62 elements were discovered. He wanted to put them in some order and wanted to verify whether there is any kind of symmetry, any kind of order, any kind of repetition in the elements. So he arranged the elements in the order of their increasing atomic mass. At that time, electron was not discovered. Electron was discovered as late as 1897 by J.J. Thomson. This is 1852. Let me exactly tell you. And welcome to this periodic table day celebration for English medium schools. As you guys know, that the periodic table I have to day switch it off. Has been, yes, this will be a obstacle. Now see, let me share my screen with a share of sound from the system. I hope you can see my screen, and yes. Why 7th February? Because in 1863, Newlands put forth the first periodic table with a law of octaves. And in fact, in US, in 2016, a chemistry teacher, maybe like me, initiated the celebration of periodic table day on 7th February every year, because to commemorate the contribution, the great sacrifice and contribution these scientists have made to make an orderly arrangement of elements so that we study them in a very simple manner and understand their properties in a very systematic manner. So this peculiar arrangement that has happened started from Newlands, who said that after every 7 elements, the 8th element is a repetition of the first element. Just like in musical octave, if you are a Western person, doesn't know about Indian saregama padhani, I will also talk in terms of the Western notes. Starts from, say, C major, C, D, E, F, G, A, B, C, D, E, F, G, A, B, then C, again comes C, starts from C, C, D, E, F, G, A, B, C. In our in Indian classical music, Sa, Re, Ga, Ma, Pa, Dha, Ni, again Sa. So that Sa is being repeated after 7 notes. That is called an octave. From the lower Sa to higher Sa. That is an octave. So I am showing you the table that he put forth, where you find there were only 62 elements. I think you are able to see the screen. Yes, raise your hands, please. Thank you very much. You guys are repeating just to give me some encouragement, because yeah, some guys are also watching directly from the YouTube, and many more will definitely join. Okay, you are able to see my screen. That's good thing. That this is the first periodic table put forth by Newlands, John Newlands. Of course, this is Newlands. Newlands. It's not. His name is Newlands. Octave that he found after 7 elements. That means the eighth element is a repetition of the first. Repetition means it's not exactly same, similar. The element will have similar properties with the first one. For example, we take this one. Here, hydrogen is coming. So I'm not taking, oh, we can start from lithium. Start from any element. Count 1, 2, 3, 4, 5, 6, 7. Then the eighth one will be repetition. Sa re ga ma pa da ni sa. So if you start from lithium, and at that time beryllium was called glucinium. G stands for glucinium. Beryllium. Then boron was called Bo. Later it was given the symbol B. Then CNOF, then Na. Sa re ga ma pa da ni sa. You start from fluorine here. Sa re ga ma pa da ni sa. So every eighth element was a repetition. Fluorine, chlorine, they belong to the halogens, having very, very similar properties, having oxidation state, valency -1, and many properties are similar. But there were a lot of drawbacks, demerits. One of them, dissimilar elements like cobalt, nickel, palladium, platinum, iridium, they also were in the same family. And in Newland's table, the similar elements were put in rows. Unlike the present day, or even the Mendeleev's table, which I will show you, the similar elements he put in a column. That column was called a group. But at his time, he was putting all these similar elements in a period. So fluorine, chlorine, bromine, iodine, they were put in one row. Lithium, sodium, potassium, and copper was there. Rubidium, cesium, all these alkali metals were there. And also you find copper, you find silver and osmium. So in any way, and that time didium was a new, element he suggested, didium. But actually later on it was found that didium is actually a mixture of two elements, praseodymium and neodymium. And at that time rhodium, Rh, was known as arrow. This is the exact table that John Newlands put forth on February 7th, 1800, 1863 in the International Committee. Now, before that, much before that, we have Lavoisier's classification of 33 elements, who included light and heat as two elements. So that, were superseded. Light and heat, they were not elements, they are electromagnetic radiations. So that was abandoned. Of course, before that, there was Dobrynin's triad. Before Newland, Dobrynin's triad, could not get any good recognition because it didn't tell about the periodicity. Just like octave, concept was given by the Newlands. The Dobrynin's triad was nothing. There were 4 triads: lithium, sodium, potassium, calcium, strontium, barium, chlorine, bromine, iodine, sulfur, selenium, tellurium. He said that the middle element's atomic mass is the average of the first and the last element's atomic mass. For example, the first one is 6.9 lithium, potassium is 39.1 by 2, the average is coming 23, and in fact, the atomic mass of sodium was found to be 23. Remember, I'm talking of atomic mass, not atomic number. Same thing is the case with all the other triads. It didn't give any idea about the periodicity, that after some fixed element, the new element will be falling either period wise or group wise. In Newland's table, it was period wise, and in after that, when Mendeleev came, group wise. Now, the interesting part about Newlands is that he died very early, 61 years. He was an Englishman. He died in the age of 61. Namaskar, Abhinandan Panda. He died at the age of 61. You do know how? He was having some minor health problem, maybe some problem like piles or fistula at the lower part. So he thought, I would invite a surgeon to his house and make a minor surgery, because fistula operation was considered to be very minor. So he invited his friend, doctor, surgeon, to operate at home. But that surgery went wrong, and he developed complicacy and had septicemia. Within a day or two, they could not control the septicemia, the large increase in WBC, and he died. He succumbed at 61 years. So he is one hero. I will tell you at the end who is the real hero in your eye. Then came the other hero, Mendeleev. In 1969, maybe few years later, he is an Englishman, Newlands, 1866, and he is a Russian. In fact, he was born in Siberia, north of Russia. So 1969, he put forth on 6th March, containing only 66 elements discovered at that time. You know, Mendeleev was a mad person. He was having 66 cards, small card, just like a card game. He was having 66 cards, and in every card he was putting the formula of their oxides of the element, each element, its atomic mass. Atomic mass. At that time, there was no knowledge about atomic number. What they were doing a serial number. So they were determining. Before that, Cannizzaro, had already given methods how to experimentally determine the correct atomic mass of element, the average atomic mass of element, that was known. So he was creating 66 small, cards, square cards, and wherever he was going, he was loving to go for a train trip. And he was taking his card box, having 66 elements and their profile, the formula of their oxides, the formula of their chlorides, the formula of their hydrides, their atomic masses, melting point, whatever was known in one card. And all 66 cards he was trying to, put to see which are similar, having similar formula of their oxides and similar other properties. Maybe melting points are not high, they're low range. So he started putting the similar elements in vertical columns. Later on, these vertical columns were called groups, unlike Newlands, who put in horizontal rows, he put in vertical columns called groups. He continued to do that and he put forth this one. And to his utter surprise, he found that unless I switch, interchange between three pairs, it cannot be a complete table. People will laugh at me. He interchanged between iodine and tellurium, potassium and argon, cobalt and nickel. He found argon was having a atomic mass 40, right? And potassium was 39. So potassium was supposed to fall below neon, which is a noble gas, and argon was supposed to follow below sodium. He said, no, 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 no. Something is going wrong. So, but he can't challenge the atomic mass that has been verified. Cannizzaro has already determined the atomic masses with precision, not as much precision as now we have done by using mass spectrometer. This precision today, the atomic mass, the average atomic mass, or the isotopic mass can be determined with a precision correct up to maybe 10 places after decimal point. So that, but maybe 1 point after decimal was also taken to be precise at that time. So he interchanged manually between potassium, he put it below sodium and put argon below neon. And same thing happened, interchanged between cobalt and nickel and potassium and argon, and then found that perfect similarity between the elements falling in a particular group was established. But the variation was on the basis of atomic mass. At that time, it was called atomic weight. I'm scared to utter the word weight because you are science students now. If I say weight, you will say weight is a force. And that should be having a unit in Newton. But we are not talking about that. We're talking about the real mass. So I'm saying not in the language they used to speak. I'm saying atomic mass on the basis of increasing atomic mass. And then he found several blank spaces. He was going on a train and he arranged them. He found there are so many blank places. Supposing here it is 20. And then he got the next one is say chromium 24. And then next one, because by that time many were not discovered, only 66 elements. So the blank places were there, and he said these elements are definitely there. We have not yet discovered. People sooner or later will discover. So now see his periodic table. There was space here below. Below boron, there was a space that was called Eka. Eka means similar. Is borrowed from Sanskrit. And it was later, in 1879, it was scandium was discovered. So in the next periodic table that he himself put forth in 1904, he kept scandium here. And then Eka aluminium, below aluminium, and boron and aluminium, and then there are two spaces. This space will be corresponding to boron, and this space will be corresponding to aluminium. Eka aluminium was actually, Eka aluminium was gallium. Gallium was also discovered. Then Eka tellurium was discovered much late. Eka silicon. Eka silicon was discovered, this is silicon here, silicon, and below that there was a vacant space. Germanium was discovered. And this Eka cesium What that was? Francium, radioactive element. Eka, manganese. What was technetium? Dewey, manganese, Dewey. Two places below. Eka means one place below. These Eka, Dewey, Tri, these have been borrowed from Sanskrit. Dewey, manganese. There was another element discovered later, uranium. Then Eka, xenon. Below xenon, another radioactive gas discovered, radon. We'll be talking about that. Now, of course, there were many demerits. Dissimilar elements were put in one group, like beryllium, magnesium, calcium. Zinc was also there. Strontium is okay. Cadmium was also there. In for sodium, lithium, potassium, you have copper, you have silver. So this, there were at that time noble gases were not discovered. The beauty is that is why the octave rule was supreme. But later on, when noble gases were discovered, all on a sudden, by again a British scientist, William Ramsay, and others, another group joined. At that time, octave rule, of course, the concept of periodicity was his idea. So we salute him, although we don't tell him the father. So when the ninth group was created, then every ninth element becomes the repetition of the first element. Now what we see is not the rule of octave, but the rule of nonave. I'm just kidding. So at that time, you find there was no noble gases. And then Lothar-Meyer gave the same thing, nothing new. Mendeleev himself in 1904 gave a modified table. During those period, 1869 to 1904, noble gases were discovered, and the main person responsible for noble gases discovery was Sir William Ramsay. So after that, he introduced another group at the left. We know that noble gas group lies at the extreme right, but he put it in the first group. So now the Newland octaves went into oblivion. Of course, the periodicity, the concept of periodicity, that the elements, they recur, they reappear periodically after certain fixed regular interval. That Mendeleev made a law that the properties of elements are periodic functions of their atomic masses. He said atomic weights. I'm saying atomic masses. And after distributing as per their similarities groups, then he gave a serial number 1, 2, 3, 4, 5, 6. And then the vacant, he missed those numbers and then suddenly went to the other, the one which will be exactly following below this. So at that time, scandium was discovered, gallium was discovered, germanium was discovered, and these also were not discovered. These were discovered much after the death of Mendeleev. So like Eka polonium was astatine, Eka tellurium was polonium, Eka iodine was astatine, Eka polonium was this is selenium, this is now Eka tellurium is polonium, this one. Eka tellurium is polonium, and Eka manganese was technetium, Dewey manganese was rhenium. This is technetium, this is rhenium. And Eka iodine was astatine. And this one is polonium, this one is technetium, this one is rhenium, and Eka cesium was discovered to be francium. So we will be stopping further discussion on the history of periodic classification. Will be coming back to that after some time. Now the time to hear the periodic table song. And then I think you are having a pen and paper with you. Maybe if you do not have, please grab a blank plain sheet and a pencil. Maybe a pencil and an eraser. We'll be doing freehand drawing, but after 4 minutes of listening to the periodic table song. I'm sure many of you must have already listened to that song. Are you able to hear? Raise your hands. Abhinandan, you just listen. The Uranium presents the periodic table song. To easily remember, 118 elements belonging to 7 periods, 18 groups, and 4 blocks. The S block in the left, the P block in the right, the D block in the middle, the transition elements, and the F block below the table, the lanthanides and actinides. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, number 10. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, 18. Potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, krypton, 36. Rubidium, strontium, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, indium, tin, antimony, tellurium, iodine, xenon, 54. Cesium, barium, lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, orbium, thulium, ytterbium, lutetium. Lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury, thallium, lead, bismuth, polonium, astatine, radon, 86. Francium, radium, actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendeleevium, nobelium, lawrencium, actinium, rutherfordium, dubnium, seaborgium, borium, hassium, metanerium, darmstadtium, röntgenium, copernicium, nihonium,
sclerovium, moscovium, livermorium, tennessine, organization 118. End of periodic table for now.
କେମିତି ଲାଗିଲା? How did you find? Okay, so what you do today, I will ask you to draw the periodic table with me. Take your blank paper, take a blank paper and a pencil or a pen, doesn't matter, and draw in a freehand manner. Keep little bit of space at the bottom and at the top and at the left, and make 7 horizontal rows, what we call periods. 1, 2, the first one has been left free. 3, 4, 5, 6. And mind you, who are watching in YouTube video, you always pause the video at the time you find it has gone past what you have not written. So you again rewind back or pause and then complete and then go ahead. I'm sure within 10 minutes we shall be writing all the 118 elements and their atomic numbers, and then study their identity, whether they're normal, natural, or synthetic, or gas or liquid, maybe metals, non-metals, metalloids, and many other things we'll be doing. So 1, 2, 3, 4, 5, 6. Oh my God. I have to make one more here. So 1, 2, 3, 4, 5, 6, 7. And I have to reserve 2 series at the bottom. These are for the lanthanides and actinides. These are the family members of one mother. So there is no space for all these 14 elements in each row that we'll be doing in one single box. Therefore, these 2 places have been taken on rent basis at the bottom. Now, after drawing this, there are 7 periods. You draw 2 vertical columns in the left. Oh my God, I'm not able to draw straight line vertically. 1 and then 2. Only 2. And then leave a lot of space. So this is group 1, this is group 2. And let us write down, this is period 1, 2, 3, 4, 5, 6, 7. This is P. P1, P2 means period. P4, P5, P6, P7. And we don't bother to write, group G1, G2. It's not necessary to. These vertical columns are called groups 1, 2. And for 10 groups, you leave a lot of space. And towards the end, you prepare 6 groups, 6 columns. So I am having a poor straight line. It doesn't look like a straight line. It looks like a curve. I tell you, don't use your scale, because freehand drawing is always better, because I am an old man and therefore I am not able to draw straight line, but you are young guys, and I can dare call you as kids. 1, 2, 3, 4, 5, 6. Oh my God. Okay, leave it. This is 6. 1, 2, 3, 4, 5, 6. This is group 13, 14, 15, 16, 17, 18. So we have 18 groups and 7 periods. And below the table, the 2 rows are a part and parcel of the main body of the periodic table. Now, have you completed? Just write down those who are watching from the YouTube and following me. They're also drawing. Yes, you guys in the Zoom, you have done, but I am wanting to interact with someone who is watching, not only watching, but also studying with me with a pen and paper or pencil through YouTube video. Please write down in the chat box, yes, have you completed the format? Oh, I think yes. Then let me sing, because maybe for your knowledge, many guys, they know, initially we thought of hiring some singer for that, but everyone said, since I myself is a singer, my passion is music, so why not I do that? I said, I am an old man, my voice will not be as much attractive as the voice of a young man. Then the audio engineer said, you do not know how AI, how the editing can totally transform the quality of the voice. So you carry on because you have the musical sense, the notes, so you give it. So the composition and the voice both are mine, but the audio mixing, mastering, music arrangement, programming, and voice recording, I mean the audio recording, editing, that has been done in a studio, JCK studio in Cuttack. It's a very good studio. Anyway, let me start. Hydrogen. You just sing with me. However good or bad it may be, maybe you can sound weird. Maybe your mom or dad who are with you may be watching. They may laugh at you. Doesn't matter. Hydrogen, helium. Write down here H and He. The first period is over. Hydrogen. Tell me. Hydrogen, helium. Sapa, sapa. Hydrogen, helium. Sanipa, sanipa. Hydrogen, helium. Over. Then give the atomic number 1 and 2. Immediately let us finish in the place just above it, the atomic number. Then comes the second period. Lithium, beryllium. Li is lithium. Beryllium is Be. Lithium, beryllium. Samare pa. Then it will again start from pa. Pasa, pasa, pa. Re dha, dhare, dhare. Boron, boron, carbon, nitrogen, oxygen, fluorine, neon, number 10. Write down. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, number 10. Give the atomic numbers. This is 3, 4, 5, 6, 7, 8, 9, 10. Then we are going to the third period. Sing with me. Have you written down? Yes. Sodium, magnesium, same. Because I have done the, this is what we call the S block. This is the S block. And this completely is the P block. And this is the D block. And this is the F block. Both lanthanides and actinides, F block. So we have given the melody, three patterns of melodies have been created. One for the S block and P block together. S block and P block together in the same period, same melody. And the other for the D block elements in the row wise. And the other is for the F series elements. So sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, number 18. Number 9, 18. So start from 11, 12, 13, 14, 15, 16, 17, 18. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, 18. Over. We have completed the third period. If by chance I'm running a little faster, you pause, because you have the option to pause and write. Then we go to the fourth period. Fourth period come across with the transition series, begins in the fourth period. So let me sing. Potassium, calcium, potassium, calcium, 19 and 20. Then another melody is coming. And you will find in the music there are 4 blank beats in the music. Then coming the upper sa. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Let me write down. Scandium, titanium. Don't make any box. Not necessary. Not necessary at all to make 10 groups. Scandium, titanium, vanadium, chromium. Tell me with me at your home. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. And we have completed 10 elements in the first transition series in the fourth period. This is period 4. Then immediately we follow. This is ending in our pa. I mean in saregama pa. Then pa sa dhare. Gallium, germanium, gallium, Ga. Gallium, germanium, arsenic, selenium, bromine, krypton, 36. Gallium, germanium, arsenic As, selenium Sc, Br, bromine, krypton. I repeat. Potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, krypton, 36. There is a number. They give the numbers. This is 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. This is 31, 32, 33, 34, 35. So we have completed the fourth period. Let us enter into the fifth period. I hope over. Anisa, over? How many of you have already remembered this song? Raise your hands. If I ask you to sing this song, entire song, looking at me, how many of you can sing the whole 118 elements in the song that have been put forth? All of you? No one. Oh, you take time. I have given you 3 months time. And then comes Jasmine, again you are here. Don't worry. Today will be repetition. Let me tell you. that there has been a change in the schedule that many of you know, that I thought there will be two sessions now. So then when I conducted similar program yesterday for Odia, then I found that 2.5 hours will be the minimum that we will require. So that will be really monotonous to continue after 2.5 hours. And I assure you who are watching, as time will elapse, you will find the discussion more and more interesting, more and more informative. So don't go anywhere. If you are going anywhere, then it should be to the restroom to answer the call of nature. You pause the video and answer the call of nature. You understand what I mean? Then come back and again join with me in the celebration of the periodic table day, knowing the elements, how they are arranged. This is called the long form of the periodic table. I will tell you the story I have kept in the middle. I thought if I continue the history part of the evolution of periodic classification, then it will be too boring and monotonous. So I switched into the latest long form of the periodic table, which was put forth by Glenn Seaborg. He is a great scientist, and he is still alive. And in US, in California, Berkeley, he was instrumental in the discovery of multiple synthetic elements. I'll tell you after some time. Welcome, Jasmine. Then coming to the fifth period, we start from rubidium, strontium, rubidium, strontium. The pronunciation has to be strontium. We often call strontium. No. You just Google search the native speakers, they have made the pronunciation as strontium, rubidium, strontium. Then comes the second transition series, yttrium, zirconium. Just it will align with the preceding element of the first series. Yttrium, zirconium, niobium, molybdenum, technetium. Technetium was discovered much later. Even during the time of Mendeleev, technetium was not discovered. So he was telling it ecatechnetium because he already arranged and given the serial number. Serial number. That the serial number will be really the atomic number, that is the charge, the positive charge present in the the nucleus of each element. That he didn't know because the electron was not discovered, proton was not discovered, nucleus was not discovered, neutron was not discovered, isotopes were not known. So in this context, it was really challenging and praiseworthy during that time, 1869 to 1900. To this technetium was discovered later, beyond 1904. Then yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. Then immediately, indium, tin, antimony, tellurium, iodine, xenon, 54, xenon, Xe. Yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, indium, tin, antimony, tellurium, iodine, xenon, 54. Let's give the numbers. These are the serial numbers. Of course, that will be called the atomic numbers later. I'll tell you the story of a young man called Moseley. Moseley was a British person. He discovered that the serial number which you guys are saying, Dmitry Mendeleev was saying serial number, and many places were vacant, and he interchanged deliberately between this argon and potassium, cobalt and nickel, and then tellurium and iodine, because they didn't match with their group properties. So that, in fact, he did not know that the variation of properties is not due to its atomic mass. Neutron has nothing to do with the property of the elements. It is the nuclear charge, the positive charge, which is same as the magnitude of negative charge. In a neutral atom, the electrons are revolving around in different cells. Those were not known at that time. So let's number them: 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54. So this is the end of the fifth period. Well, those who are repeating today, some of the Odia guys, I had invited them to listen to me talking in English throughout the session. And they will also revise, and their confidence level will still grow. Then comes sixth period. Again, I am singing, just like Pythagoras said that every planet, every moon, the sun, the stars, everyone has a particular vibration, a music, is sending a musical note. Similarly, all elements also have a musical note. I have attempted to put it in a proper musical note. Let me see, time will tell if this will be accepted not only in Odisha, but also in India and elsewhere in the world. There are multiple periodic table songs. Maybe many songs from India have gone up to 20, atomic number 20, or maybe max 30. But all 118 elements, only one a society has done, that is an American society, ASAP. Perhaps this is the second one, the Uranium, which has produced a similar, not similar, a periodic table song. Absolutely, you can listen to that. There is no similarity. No, absolutely no similarity. I thank from the core of my heart to my eldest granddaughter, Myra Tripathy, who gave me the piece of music, and he said, JJ, they call me JJ. How do you like it? I said, it's wonderful. I said, I will be producing for Indian students and maybe for all. That could be materialized with the divine, interference that has come true. Yesterday we had it. Oh, I forgot to tell you that in the evening, 6:30, we'll have a program. My colleague, Dr. B.N. Das, will be discussing on the periodic properties, how the atomic size, the ionic size, and the ionization energy, enthalpy, the electronegativity, the electron affinity, all this vary across a period, along a group, and they're trained. I have instructed him not to waste time on the reasonings, why it has happened. It will take a long time, and in 1.5 hours program, 6:30 to 8, it will not be possible to. I have told him to show you the graphs, because you guys are 9, 10, 11, 12. You can understand if the trend of variation of size or anything, any physical property, is shown to you in form of graph or in tabular form, and discussed how it varies. Okay, coming to the sixth period, we have cesium, barium, cesium, barium. Then comes, this is 55 and this is 56. Then comes lanthanum, La, below yttrium, lanthanum 57. But lanthanum, being the mother, has 14 children. Now, I forgot to tell you that Mendeleev had 17 siblings. You understand what are siblings? Brothers and sisters. He was one of them. And out of 17, 3 died during birth. And 14 remained. So he was among one in the 14 siblings. And out of all the 14, he was a brilliant chap from the very beginning. And his mother took so much of care that he brought Dmitri. Mendeleev was the title, just like Patnaik. So Dmitri, he brought Dmitri from far Siberia region to Moscow to get admission into one of the best schools there. And then he got into the best university. And during his studentship, he wrote a book on organic chemistry. Organic chemistry. He wrote, and it became very popular. And he got selected as he finished. He got selected as a professor of that university, great university, and earned international name and fame in chemistry. Particularly, he was known for the arrangement of elements in a particular patterns, those that is called the Mendeleev's periodic table, which was little short. I showed you. I didn't like to spend more time. It was having, 8 groups at the end when noble gases were discovered, and 12 periods. I mean, this thing. So that was modified, and then Seaborg introduced this long form. In fact, the Berry, a friend of Bohr-Berry scheme, the Berry was the person who told the concept of transition, because you will later know that in these the electrons enter into d orbitals. So either from 8 to 18, the cell expands from 8 to 18 or 18 to 32. So this falls enter into the d orbitals. Therefore, they cannot be put under the main groups. The criticism that copper, silver, they are coming in among sodium, potassium, lithium, so that could be overcome by knowing, when electronic configuration was known, that these elements have their electron entering into the d orbital, then they found a middle portion where these elements could be arranged. And then Seaborg formally gave this long form. Then coming to the song part, lanthanum has 14 children. So nowadays, lanthanum is not put here. It is put at the bottom, 57. There is a controversy, even in US, some conservationists, old-timers, they say, don't bring lanthanum below the table. Keep lanthanides as 14 elements. Don't make it 15. But majority of the scientists say that let us skip this place vacant and bring lanthanum to the bottom, indicating that lanthanum is the starting element of lanthanides. So, majority opinion is there are 15 lanthanide elements from lanthanum to lutetium. Let us sing. Lanthanum, cerium, praseodymium. Lanthanum, you tell me with me. You sing lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. No, these lanthanides are also called rare earths. Rare earths, oh my God, where did you go? Are you here with me? Yeah, lutetium. I repeat, La is lanthanum, C cerium, Pr praseodymium. In the description box, you will find a link where you get everything in details. After this, we shall be only speaking, listening, not writing anything. But you will be getting everything in order in that handout, whose PDF file, the link I have given. You will download that. Lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, EU, gadolinium. Gadolinium is my favorite element. Why? Because of multiple reasons. One of them is that it is used, the gadolinium compounds are used in the form of injection while we enter into a MRI machine. Have you ever gone to an MRI machine? Going, you have seen in the picture that somebody is sitting, lying down flat, and the nurse will give an injection. That is gadolinium injection, and because that will be helping to take the image properly, and he will be slowly entering into that big cylindrical place inside that instrument, where there is some lot of sound. I had experienced about 1 hour remaining inside that MRI machine, right? So gadolinium is used there. Terbium, TB, gadolinium, terbium, dysprosium, holmium, HO, erbium. It is ER, but it will be pronounced as erbium, thulium, THU, and all the words, the spelling have been listed, and I have given them. Erbium, thulium, ytterbium, 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 lutetium. Then you give the number 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71 is lutetium. Then come back to the D series. Come back to the D series. Now then again we have to sing with lanthanum in the same pattern. Therefore I have kept lanthanum in 2 times, because the pattern will be same. Sa pa, scandium, titanium, yttrium, zirconium, lanthanum, hafnium, tantalum, tungsten, lanthanum, hafnium, tantalum, tungsten, rhenium. That is Dewey manganese. Dewey manganese. Two places below manganese is Dewey manganese. Rhenium, lanthanum, lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury. Gold is AU and mercury is SG. The symbols you all know because you are class 9, 10. Mercury. Then immediately after that, thallium, lead, bismuth, Bi, bismuth, polonium, astatine, PO, astatine, radon 86. Are you able to see? It's not being erased. It's very peculiar. BI. This is BI. And here in the Delhi news, you might be tracking that Aam Aadmi Party has lost miserably, and Kejriwal also has been defeated from his New Delhi constituency. So BJP is now going to form the government. So thallium lead bismuth polonium astatine radon 86, then give the number. The 71, this will be 72, because after lutetium this hafnium comes. So hafnium onwards, they're called post lanthanide elements. Post lanthanide elements. After lanthanum, post lanthanide element starts from hafnium. 72, 73, 74, 75, 76, 77, 78, 79, 80, then 81, 82, 83, 84, 85, 86 already we have done. So we are only left with one period. With lanthanides is over. Then we have to complete the actinides. In general, it's written AN. Lanthanides, actinides. Lanthanum is La, is one element. I call it the mother. And 14 children, just like 14 siblings of Mendeleev. But Mendeleev was one among the 14, because 3 of his siblings died, unfortunately, during birth. So 14. So that 14 and 1, I'm taking the mother of all the 14 children. One of them maybe gadolinium. Let us take my favorite gadolinium as Mendeleev. I don't remember what was the position in the hierarchy of the 14 living children of the father Mendeleev. Okay. Then let's start singing the 7th period. Francium, radium, samarepa. Francium, radium. The radium, the same radium which Marie Curie and Pierre Curie, they had discovered. Francium, are, radium. This is 87 and 88. Then comes the actinide series will come. 89. It should be written here. In the previous books, you will definitely find actinium 89 will be here. But nowadays, they are not writing here. They are making a blank space. There, they are writing 89 to 103. All the 15 elements, they are called actinides. So let us bring actinium here, 89. Then let us sing the same pattern of lanthanides. Actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, Hormium, Mendeleevium, Nobelium, Lawrencium, Actinium, Thorium, Protactinium, not Palladium is here, Pa. Actinium, Thorium, Protactinium, Neptunium, that is pronounced really as Neptune, Neptunium, Plutonium, Americium, curium. Now, Neptunium, plutonium, americium. Now something has gone wrong. Actinium, thorium, protactinium. Oh, actinium, uranium. Oh. Our group, our organization is named as Uranium, but I have left my group. This is so very bad. Uranium, Actinium, thorium, protactinium, uranium, neptunium, Np, plutonium, americium, curium, berkelium, bk, californium, Cf, einsteinium, formium, Fm. Here yesterday I made a mistake here. By mistake I wrote Cu. Copper is here. This is Cm, curium. Curium, berkelium, californium, einsteinium, formium, mendelevium, nobelium, No, lawrencium. Actinium, thorium, protactinium, uranium, neptunium, plutonium, plutonium, americium, curium, berkelium, californium, einsteinium, formium, mendelevium, nobelium, nobelium, mendelevium, Californium, Einsteinium, Formium, Mendelevium, Nobelium, Lawrencium. Then give the number 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99. 100 is Formium, Mendelevium is 101, and Nobelium is 102, and Lawrencium is 103. Then coming back, these elements 104 will be called the post-actinides, post-actinide elements. These from hafnium onwards, they are called post-lanthanide elements. These will be post-actinide elements. They are also called super heavy metals, super heavy elements, not metals, elements. Super heavy elements are those which are above and after actinides. Post-actinide elements are also called super heavy elements. Please bear with me. I'm feeling some fuel. I'm feeling some fuel because we have so many interesting. Then we'll be back to here. We'll be singing in the same pattern. Sapa, lanthanum, hafnium, scandium, titanium, yttrium, zirconium, actinium, rutherfordium, dubnium, seaborgium. That Seaborg. He was the latest scientist who got Nobel Prize and who was instrumental in the discovery of many elements, including this seaborgium, borium, actinium, rutherfordium, RF, dubnium, actinium, rutherfordium, dubnium, seaborgium, borium, hassium, meitnerium, dumstatium. This meitnerium will be below iridium. Oh my God, what happened to my... Yes. Hassium, meitnerium, empty. Dumpstatium, DS, below platinum. Roentgenium, copernicium. I am writing again. Actinium, rutherfordium, dubnium, seaborgium, borium, hassium, HS, empty. Hassium, meitnerium, dumpstatium, Roentgenium, copernicium. All these spellings I have given, nothing to worry. Nihonium, NH, flerovium, muscovium, livermorium, tennessine organization 118 OG This is OG. 118, that is the end of the periodic table. Actinium, Rutherfordium, DB, so 105, 106, 107, 108, 109, 110 is Darmstadtium. Roentgenium 111, Copernicium is 112, then 113, Nihonium, Plerovium is 114, then Moscovium is 115, Livermorium is 116, Tennessine is 117, and Organechon is 118. So we have completed. And if you make a dividing line below boron, a stair step, one horizontal, one vertical. I'm sorry. One horizontal, one vertical. One horizontal, one vertical. One horizontal, one vertical. So this is the dividing line, the stair steps to separate between metals and non-metals. To the left of this stair step are metals, and to the right, these are non-metals. But those which are in the vicinity, close to the stair steps, they are metalloids, having some metallic character, some non-metallic character. So, among the first grade metalloids, boron is close to this stair step, silicon, arsenic, germanium, antimony, tellurium. And I'll tell you, polonium and astatine are scarce element. They are available in nature almost extinct. Nowadays, we are preparing polonium and astatine synthetically. And yeah, I forgot to tell you, tomorrow will be a very important lecture by me because I shifted. We are celebrating 3 days. Tomorrow, I will be talking about the radioactive elements and how they are synthesized. During that, I will tell you many more things. I understand that you guys have your annual examination starting from 15th, and the board examination class 10 is starting from 15th. And despite that, you guys are attending. That's a great thing. That should be the spirit. For class 10, it is okay. They are supposed to be serious, little more serious than what you are. But the class 9 to 10 jumping is spontaneous, doesn't involve any excitement or any anxiety. Now, in the second grade metalloids, they have been included now carbon, aluminium, selenium, and this polonium and astatine. Now, this is just for the sake of names. Polonium, astatine, they are almost extinct in the nature because they are radioactive elements having very small half-life periods. They have died. But for our purpose of nuclear reactions, we are producing polonium and astatine. I will tell you tomorrow how. Now, these are the gaseous elements 11, nitrogen N2, oxygen and ozone O2 and O3, fluorine F2, and all the noble gases, helium, neon, argon, krypton, xenon, and radon is radioactive. Organechon is also radioactive. Now, these are, and hydrogen also is a gas. And to me, there are two liquid elements. One is a metal, that is mercury, and one is a non-metal, red colored liquid is bromine Br2. But in India and other hot countries, we also include potassium, rubidium, cesium, and francium. I'm sorry, rubidium. I'm so sorry. Rubidium, cesium, and strontium, as well as gallium. You can play with gallium because that is not a very dangerous chemically reactive element. You can just hold gallium in your own hand. You try to watch the video again and again. We have given a catchy graphic. In gallium, we have given that gallium metal has been, someone is holding in his palm, and in the palm it will melt because its melting point is very, very low, 30 degrees Celsius. And our temperature is 37, nearly 37. So when you hold it in hand, even if you are staying in a cold country, even if you are staying in a cold country, like I was there in California, where the temperature was very temperate. It was 15, 16 degrees Celsius, and in the winter, it doesn't drop down much. Max is 10 degree. So in that, your body temperature is always 37. So when you hold in your hand, you will find it will melt. But same thing will happen for cesium. Cesium is again 30, but don't hold it in your hand. It's very, very reactive metal. So put a glove, and then put it. You will find, on your glove, it will be melting. So also rubidium is 37. It will melt a little late. Cesium will melt a little early. So francium is a radioactive element and a scarce element. It will not be found much. Like astatine and polonium, you will not find much of francium. It is being prepared. Now, the time has come to tell you how many natural elements are there which has been produced by the nature and how many we are producing. We mean scientists. Now, up to plutonium, 94 elements are natural. To me, 94 elements are natural. Traces of neptunium and plutonium are there in the nature because they're, I will tell you tomorrow, their, descendants are there. Because of their smaller half-life periods, they have died, and we are now synthesizing it, but still it is there in trace quantities. So all of them, and just put a line, put a star after bismuth. After 83, put a star mark. 83 up to 83, the elements are stable. And above 83, all the isotopes of all the elements are unstable radioactive. They emit from their tomies. Tomies means from their nuclei. The singular is nucleus. They emit alpha particles, beta particles, gamma rays, positrons sometimes, lighter ones. So these are harmful radiations, alpha, beta, gamma. And then continue to put star mark. These are naturally radioactive. They are found in nature. Of course, they are now found in very trace quantities. Astatine is the least abundant element. So next, polonium. Radon, we put a namaste because radon is a pollutant gas. It is a radioactive gas. It is created in uranium and thorium ores, and in some places where the deposits are there, radium, because radium, radium 226 is its mother. There are many radium deposits in many places, particularly in US, India, yes. So the moment a radium isotope, we'll talk about isotope very soon, emits an alpha particle, then it is converted to radon. Then it becomes a gas, it has a wing, and it flies and enters into our atmosphere through our home. From inside our home, radon is now inside our house. There's maximum in US. And of course, every harmful radiation like alpha, beta, gamma. Gamma is not a particle, it is an electromagnetic radiation, a photon of high energy. But alpha, beta, they are particles. We'll talk about that after some time. So, they are harmful radiations, but within a certain limit, all of us are potentially a radioactive source, because many things that we are eating, carbon containing, out of the three isotopes of carbon. By the way, what are isotopes? Who can tell me? Isotopes, who can tell me what are isotopes? Yes, from outside. Isotopes actually are the same elements. The elements are same, but their neutron numbers are different. Supposing I write carbon has three isotopes. Carbon, has three isotopes: C12, C13, C14. And in the nature, you find its abundance is very, very, this carbon 13 is only 1.08%. So 98.92% is carbon 12. And this is stress. If the percentage goes to 10 to the power minus 5, minus 6, minus 7, minus 8, then that is not counted. So stress. But this is radioactive. Its tummy emits beta particles. Beta particles. Actually, beta particles are nothing but like electrons. Like electrons. But the question is how an electron, which is a beta particle, comes from the nucleus. It is because inside the nucleus, a neutron changes into a proton and a beta particle. So you just add up the lower ones, which are charges, +1, -1 will become 0. And 1 plus 0, electron has negligible mass compared to proton and neutron. Although it has mass, it is a mass possessing a particle, but it has negligible mass compared to proton and neutron. We write 0. So this is called beta. The symbol is given is beta, but it is exactly the same as an electron, which is produced inside the nucleus by the conversion of one neutron to a proton. And this beta particle goes out of the nucleus with high speed. Very, very high speed. But of course, less than the speed of light, but comparable with the speed of light it goes. And as a result, since one proton becomes more, the new element, the same element will not be there. It will die. The moment it will produce a beta particle, the new element, who can tell me what is the new element? You devise first what will be this, so that its sum with -1 will be equal to 6. It will be 7. 7 minus 1 is equal to 6. And 14 minus 0 is equal to 14. And what is 7? You have to look to the bottom, that is the atomic number, the nuclear charge, to identify the isotope. So this is nitrogen. So 7 is nitrogen, normal isotope 14. So this beta goes out of the nucleus. So, but this is carbon 14, the half-life period is very high. Not very high like uranium 238 or thorium 232, 5,770 years. To make the initial amount to become half, you need this. Same time will be required to become half of the half. Same time will be required to become half of the half of the half. So it is independent of the initial amount. That's why it remains for a longer time. And our body, because we are taking food containing carbon, organic compounds contain carbon, we are also carrying carbon 14, which is emitting beta radiation coming out from our body. It has a very high penetrating power. Not as much penetrating power as gamma, but penetrating power. And in many fruits, many vegetables, and in banana, we are taking a lot of potassium. Do you know potassium has two natural isotopes? One of them is stable, 39. The other one is star. Other one is radioactive, and another one is there, 41, that is stable. Now see the magic of nature. One of them, the middle one, 40 isotope, is radioactive and is a beta emitter. Just like carbon 14, it is a beta emitter. And here there are how many neutrons? So 0 minus 9, 1, 3, 1, 2. 21 neutrons. Here it is 20 neutrons. Here it is 22 neutrons. So only one neutron variation. This makes stable, and because these are present in such a small quantity, the average atomic mass is 39. Because you know how to calculate the average atomic mass of polyatomic species. For example, you have chlorine. You already know, needless to say, chlorine has two isotopes, 35 and 37. In the ratio 3 is to 1, 75% is to 25%. So we, for calculation, we do not use 35 or 37. We use 35.5. Well, what is 35.5? No, these are isotopic mass number. The actual isotopic mass will be close to 35, 34.9 something, 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 something. So because when we measure isotopic mass in a mass spectrometer nowadays, relative to carbon 12 as the standard, you will not get a whole number. So whenever you find the atomic mass is coming close to a particular whole number, close, that means 34.99 something something, then close your eyes and say that the nearest whole number is the mass number of that isotope. So this is the isotope you are talking about. But there are some monoisotopic elements. Nature has given only one isotope, not more than one isotope. So in that case, we can't get any average. The isotopic mass is the atomic mass. But here, the average atomic mass, as you find, I am just revising it. Average atomic mass is equal to 3 into 35 plus 1 into 37 by 4. It is coming nearly 35.5 that we use. Similarly, the elder sister of chlorine is bromine, 3579, bromine 3581. The nature has given in the ratio 1 is to 1. See how the nature discriminates between the sisters. And the youngest sister is monoisotopic. Isotopes only differ in the number of neutrons. They have the same atomic number, but different mass numbers. Monoisotopic doesn't have any other isotope. Similarly, the eldest sister, that is 127, is also monoisotopic. See, we are really intrigued by the handiwork or the planning of the nature, that the middle sisters, they are polyisotopic, and none of them is radioactive. This is stable, this is stable, this is stable, this is stable, and its average atomic mass will be exactly 80, because 1 is to 1, 79 into 1 plus 81 into 1 by 1 plus 1, 2, so it will be 80, as if it is a number average, but actually it should be a weighted average. The percentage abundance of each isotope has to be taken into consideration to find the average. Now I'm telling you that teen, and I have given you, I have meticulously prepared this table of isotopes. How many, you will find isotopes are also called nuclides. Particularly they are applicable when we talk of radioactive elements. Now, supposing 10 has the maximum number of stable isotopes, 10 isotopes, 112, 114, 115, 16, 117, 118, 19, 20, 22, 21 is absent, 24. And with the different percentages, 0.97%, all are percentage, 0.66, 0.34, this is 14.5, 7.68, 14.2, and in this we find the average, because it is percentage divided by 100, so the average that we use in stoichiometric calculation is nearly 119. The data given for teen is 119, actually it is 118.71. So there are some, I have given a list of all the 118 elements. In one column, I have given the number of stable isotopes, stable, whose tomies are perfect. Is not vomiting out any alpha, beta, gamma, positron, nothing. And this column is for radioactive isotopes. Natural. I'm not talking of in synthesis. Tomorrow we shall see. For every element we can prepare many other isotopes synthetically. We'll talk about that. So you will get a detailed list of all the elements, and you will find there are 20 elements which are monoisotopic. These 20: beryllium, fluorine, sodium, aluminum, phosphorus, manganese 55, cobalt 59, and the cobalt 60 isotope that is used for cancer treatment is a gamma source. I'll tell you how gamma is produced. Gamma is not a particle. Alpha is a particle. Alpha is a particle. For example, I'll give you, I have shown you the emission of beta. It will be worthwhile to say you how an alpha particle, supposing I'm talking of uranium 238, which is an alpha emitter. Who can tell me what is an alpha particle? Many guys are watching from the YouTube, and we have already 2 hours. Maybe I told you that it will be 2.5 hours. We will be getting a lot of information, because I will be concentrating on those who will be watching now, and also more will be watching later. Yes. Write down in the chat box. Write down in the chat box. Yes. Yes. It is helium double plus. Helium has atomic number 2 and mass number 4. It has 2 protons and 2 neutrons. So if you remove 2 electrons, it becomes a dipositive helium ion. This is nothing but an alpha particle, which comes out of the nucleus, just like a beta particle comes out by the transformation of a neutron to a proton and then beta particle. But here no transformation is required. The protons and neutrons are available inside the nucleus. So 2 protons and 2 neutrons, they group together and come out in the name of alpha particle. So the symbol for alpha particle is He24. This is the charge. If no sign, it is positive charge, and only beta particle has -1 charge, and 4 is the mass number. You can subtract. 92 minus 2 is 90. 238 minus 4 is 234. And look to the bottom number. That will give you the identity. 90 is thorium. After, actinium, then thorium. So this is alpha particle that goes out with a tremendous speed. So what I was saying, these are the 20 monoisotopic elements which I have highlighted in red, which have no other partners. But there are many others which have one or two or only one radioactive, along with one stable, like vanadium has one stable and one naturally radioactive. So I have highlighted them in blue. You'll find vanadium, you'll find uranium has one, and indium has one, lanthanum has one, lutetium has one, and so many others like that. Let us come back to the aim to end the periodic table. We have the metals, the non-metals, the metalloids. I told you that nowadays, yesterday some teacher asked me that can we include, where is that? Yes, can we include polonium and astatine as metalloids? I said yes, for the sake of including, you do that. But where is polonium? Where is astatine? They are almost extinct. So much of efforts, money, expenditure is incurred to synthesize polonium and astatine, but it's not available in nature. We hardly find polonium and astatine in the bulk state. Let me tell you, let us continue to put star. Radon is radioactive. Radon is always present in the atmosphere. It is increasing in amount because of the decay, the decomposition, the decay products of uranium and thorium ores present inside the earth. So nobody is daring to synthesize radon. Radon is a pollutant gas, the harmful radiation. It is increasing, so nobody is synthesizing radon. But polonium is required. Polonium is synthesized, astatine, francium, put a star, radium, put a star, actinium here, because we have written actinium here, actinium, made a star. All these are radioactive up to plutonium. Up to plutonium, natural. Then also star, these are synthetic. I have written everything in my handout, so you need not bother about writing so much. So up to, many books you will say up to uranium, 92. But most importantly, Shiv, you remember that below bismuth, there are two elements which are radioactive. That is technetium, put a star mark, 43. Nowadays, it is prepared. It is now in the nature extinct. It is now being synthesized. I'll tell you how. And then promethium here, PM61. So they were there. They are there in a very trace amount, but we are synthesizing it for our medical purpose. They're being used for medical diagnosis, cure of cancer, and PET SPECT scan is being, imaging is done by use of the technetium-99 isotope, which is being synthesized. So technetium-43, promethium-61, they are the two which are radioactive. There is no stable nuclide. Whatever was there in the nature, they are gone. We are preparing it, right? And all after bismuth, polonium, astatine, radon, francium, radium, actinium, thorium, protactinium, uranium, neptunium, plutonium, up to plutonium, natural. But now we are synthesizing neptunium and plutonium because they're available in trace quantities in nature. We don't depend on that. We need a lot of plutonium for our nuclear power plants. So we are synthesizing neptunium and plutonium. Plutonium is really synthesized via neptunium. So we are synthesizing now. So for me, 94 elements, all are natural. They are their interest quantities. Some people say there are 88 elements, there are 90 elements. Uh, they exclude neptunium and plutonium. They say 92 are natural. Some people exclude another two, like polonium and astatine. And some people exclude francium, 87. So there are so many controversies running in the market. But we will not enter into controversy. But make sure that francium is almost gone. Radium is there. Radium is being synthesized, but its ores are there in the uranium and all different, I'll tell you tomorrow, they are available. So synthesis is not required. Actinium is being synthesized. Thorium ore is abundant. The future of our nuclear energy is thorium. Abundant. So thorium, uranium, they are not synthesized. But actinium is synthesized, protactinium is synthesized, they are scarce naturally, and so also neptunium and plutonium. So these are the elements which are natural but also synthetic, which starting from polonium, astatine, radon, namaste, nobody ventures preparing radon. It is always being created every time from different decay processes. Then francium, then radium, they are preparing, but it's not required. Then actinium, protactinium, neptunium, plutonium. And uranium, thorium ores are abundant. Thorium ores are abundant. I will tell you tomorrow that how thorium will be the future of the nuclear energy. Now coming to the electronic basis of the classification, let's talk the elements group wise. This is group 1, excepting hydrogen, which is very unfortunate to have any fixed place. It can be placed in group 1, group 7. Some people say it can be placed under group in the carbon family. So there are some similarities. So hydrogen, I say it is a one-member group, just like a set can have only one member. So similarly, hydrogen is a one-member group. Forget about hydrogen. Then these are called alkali metals, group 1, lithium, sodium, potassium, rubidium, cesium, francium. You can give some magic numbers like 8, 8, 18, 18, 32. After 8 elements, you get, add 8 to 3, 11 will be sodium. Add again 8 to 11, it is potassium. Then add, because transition series has come, add 18 to potassium, it will be 37. Then add again 18 to 37, it will be 55. And finally, since F, the lanthanide series have come, all the 14 elements have come, you have to extra add 14 after 18. So 32, if you add to 55, you'll get 87. So these are called the magic numbers for the S block. Same thing will be the case, 8, add 8, then again 8, then again 18, 18, 8, 8, 18, 18, 32. You'll get. Or if you get 11, this is 12, this is 19, 20, 37, 30, 38, and so on. But we have already done in our song. And in the P block, since transition series are coming, the magic numbers are 8, 18, 18, 32, 32. 1 8 is missing and 132 is increasing, because boron, you add 8, 13 is aluminum. Then don't add 8, because already 10 transition series has come. So add 18. So 13 plus 18, 31 is gallium. I told you in India, gallium is called a liquid. But in Canada and Northern America, they don't care about rubidium, cesium, francium. Francium is present in a very scarce quantity. Who will be, bringing a large amount of francium and see, yes, its melting point has been studied, scientifically studied. It is lower than, it's almost similar to cesium. And what I was saying is, what I was saying, what I was saying, what I was saying. Yeah. What I was saying. Uh, Magic numbers of P block. Yeah. 8, 18, 18, 18, 18, 18, 32, 32. So then add another 18, you will get indium, 49. Then 32, 81 thallium. Again, another 32 is nihonium. So once you get all the, this is 5, 13, 31, 49, 81, and 113, then you go serially. 5, 6, 7, 8, 9, 10. 13, 14, 15, 16, 17, 18, 31, 32, 33, 34, 35, 36. But we don't need it. We have done in our song, periodic table song. And then connect. This is 20, this is 31. Then you continue 21, 22, and connect between 38 to 49. Then 39, 40, 41, 42 up to 48. Then 56, 57. Remember, 57 has 14 siblings down the table. So go up to 71. Then post lanthanide 72 to 80. Then after actinium, go to actinides from 90 to 103, including actinium 89 to 103. Then come back to Rutherfordium 104 and so on. Now, the only reason behind the similarity in properties of elements belonging to a particular group is their electronic configuration. All these alkali metals, they have one electron in their valence shell. If you are not a class 11 student, this will be, that electron will be present in the s orbital. And in general, it will be called NS1. This is 2S1, this is 3S1, 4S1, 5S1, and so on. The cells will be more and more, but in the s orbital, only one electron. So that can be lost. And the only oxidation state or valency for all these metals will be +1. Cannot be +2 or +3. Because we have only one electron that has to be lost. You can't, pluck out electron from the stable octet. Once it loses one electron in the outermost cell, lithium will be having helium configuration. Duplet is very stable. It's very, very difficult to remove electron from the stable duplet or octet configuration. Similarly, the alkaline earth metals, the group 2, they have 2 electrons in their valence cell. In general, NS2, 2S2, 3S2, 4S2, 5S2. Therefore, the valency will be +2. Cannot be +1, because if one electron is lost, the other electron will jump automatically to attain this nearest noble gas configuration. So, +2. Similarly, this is group 13. They have got 3 electrons, and one of them is in the P. This is NS2, NP1. This is 2S2, 2P1, 3S2, 3P1, 4S2, 4P1. Of course, 3D10 is gone, but we don't bother about 3 is an inner cell, 4S2, 4P1. So the last electron is present in the P. And all this is P2, P3, P4, P5, P6. Therefore, all these elements, these 6 groups from 13 to 18, previously these noble gases were called group 0. Long ago, when this classification 1 to 18 was not there, we were saying 1A, 2A, this is 3A, 4A, 5A, 6A, 7A, group 0. And this is group 3B, 4B, 5B, 6B, 7B, 8. These 3 columns together was group 8. VII. And this is 1B copper group, and this is 2B, the zinc group. Nowadays, that naming system is gone to dogs. So we have, this system. So who can tell me? Now, see, up to Californium, put a line here. Up to Californium, the scientists have successfully prepared some large quantity, maybe milligram quantity, so that they can hold it for some time. Because of their little more half-life periods, they can hold it and they can keep it as a target to fire accelerated particles onto it. To tomorrow we shall know, and then make a transmutation to another element. So up to Californium 98, the scientists have prepared the elements in bulk. Some larger amount, maybe few milligrams, gram amount. I'm talking of neptunium to californium, and about actinium and protactinium. Thorium, abundant. Uranium, abundant. And then, after californium, is Einsteinium, it is gone, ES, Formium, Mendeleevium, Nobelium, Lawrencium, then Rutherfordium, Dubnium. And as you go farther and farther from Californium, you will find the amount of substance, isotopes produced, maybe ranging from few atoms. Organization, only one atom was created at a time. One atom, this organization. And that too, its half-life period is some millisecond. But don't worry, they are not telling lies. There are three groups who are at internally at daggers drawn. They fight with each other, but they also love each other. Three groups. One group is at Rasa Dubna near Moscow, where there is a cyclotron device where they take a target static material that has to be in bulk quantity, and a projectile, a positive ion like helium ion, like calcium 48, and so on. They will put it in a cyclotron, which is a spiral shape, and with the help of magnetic field and electric field, they will accelerate it to a very high speed, and they will hit on this target and see what changes are taking place. And by this technique, they have synthesized all these elements: neptunium, plutonium, americium, all. Out of them, fortunately, up to californium, since they have life periods, they are little relatively more stable. I'm not saying they are stable elements, they are radioactive, relatively more stable, so they can have some good amount to make them target and produce heavier elements, super heavy elements, trans-actinide elements like rutherfordium, dubnium, seaborgium. These have been prepared in very, very small quantities. Maybe some microgram, maybe some few atoms, 10 atoms, 100 atoms, 2 atoms, 1 atom. So they cannot be used as targets. Unless you have a bulk quantity, they cannot be put and have a reasonably long half-life period. They cannot be put as a target for other projectiles to hit on with high speed. So we are almost going to end our program. So I told you that this is 13. There are 3 electrons in the valence shell. The maximum valence is +3 and the minimum is +1. You will be knowing thallium can have both +1 and +3, because if one electron will participate, it will be +1, because NS2 NP1. If only NP1 electron will participate, then it will be +1. If all the 3 electrons will participate, it will be +3. Similarly, carbon is both +4 and -4. If all the 4 electrons will be donated, will be lost, of course, it is covalency, oxidation state, then it is +4. If it will gain 4 electrons, it will also attain the nearest noble gas neon configuration. If it will lose 4 electrons, it will gain the helium configuration. So +4 and -4. Of course, some other oxidation states like +2 is there in carbon monoxide. And nitrogen can lose 7. Nitrogen, cannot lose 7 electrons. It cannot show a +7 state. But others like phosphorus a +5. I'm so sorry. It is the fifth. 15 means 5a. There are 5 electrons, Ns2 and P3. So nitrogen can show oxidation state of +5, but it cannot show the covalency of 5. There is no nitrogen pentachloride, because for that to happen, the lone pair has to be unpaired and to occupy a vacant d orbital. There is no d orbital in nitrogen. Well, you are a 9th class student, nothing to worry. I'm just sounding you just for sake of information. Now, but others, PCl5, arsenic pentachloride, so can go to maximum +5 because it has 5 electrons. Either it can lose completely or share 5 electrons as a more electropositive element, so +5. And if it takes 3 electrons, and you takes 3 electrons, so it will be having -3. So the minimum is -3 and maximum is +5. And in between, it can have +3. If only 3 electrons in the P will participate, then +3 and -3 if 3 electrons will be gained. Similarly, in the oxygen family, which are called chalcogenes. Chalcogenes comes from the word chalcos, which is copper. Copper ores, they contain a lot of oxygen. So, and this is nicogenes. Nitrogen family members are called nicogenes. This is primitive name. Oxygen is chalcogenes, and this is halogens, salt forming. So oxygen family will have a maximum state of +6 because they have 6 electrons in their valence shell, Ns2 and P4. Oxygen cannot show +6 because it doesn't have a vacant d orbital. So it will maximum go to +2 and -2. By gaining 2 electrons, it will attain the nearest neon configuration. And by losing, by sharing 2 electrons, it can also have +2. It can share because it has got 2 electrons to share. And fluorine is either the family is this +6, then you can have -2. And in between, you can have +2, +4. And fluorine, the maximum is +7 because it has 7 electrons. Not fluorine. Fluorine has also 7 electrons, but it cannot show any other state than -1. Because it is the most electronegative element and doesn't have a vacant d orbital, and therefore it will gain 1 electron, will become fluoride ion, so -1. But all others can go up to +7 because they have vacant d orbitals. And minimum is -1, and in between it can have +3, +5 also. And these noble gases, which were once considered to be really inert, but nowadays many interesting compounds have been synthesized. Xenon has produced a large number of compounds showing oxidation state from +2 to +4 to +6 to +8. All the 8 electrons, octet, all the 8 electrons take part in producing compound like xenon tetroxide, where xenon is in the oxidation state of +8. And there are several such compounds. But neon doesn't show much compounds, so also argon. But even helium has been used to form a binary compound, helium hydride. So no longer they are inert. Yes, they have stable configuration, more stable than the others, but they can be converted to compounds. So now the time, I'll show you what I have missed out from this thing. I've talked about groups. Yeah, about the transition groups, they have their electrons in the D. This is the D1, 3D1, 4D1, 5D1, and so on. This is D2, D3, D4. There is some anomaly. It will be D5, D5, D6, 7, 8. So these groups have their electrons in the d orbitals, same number of electrons in the d orbitals, so they behave similarly, and you'll find the elements, they behave similarly period wise, I mean row wise as well as group wise. These commonly called d block elements. And zinc, cadmium, mercury, they are not true transition elements. They are, but they are not true transition elements because they don't have anything, any space to remain. So they are there in the D block, but they are not transition elements. Remember, transition elements will have a variable valency, and in one of the ions, they should have incomplete D subcell. So there is no ion Zn2 plus, Cd2 plus, although mercury has two valency, mercurous plus 1, mercuric plus 2, but it goes from S6s1, then 6s2. Nothing to do with D. D orbitals are untouched. So therefore, they are not true transition metals. So also to some extent scandium. Scandium doesn't show any variable valency. It has only one valency plus 3. So they are not true transition metals, but they have to be there. Now coming to this one, we have already done electronic configuration, and these lanthanides and actinides, these have their element, the last electron in the f orbital. This is in the 4f orbital. This is in the 5f orbital. And there is a group of scientists who say that don't bring lanthanum and actinium down. Keep it there. Don't change. Don't change. They say the lanthanum and actinium, they have electron in the D. They do not have any electron in the F. So why you are keeping in the F block? Then the counter argument that others do in favor of this, they say lanthanum is the mother of all lanthanides, because all the elements, they are found along with lanthanum in lanthanum ores. So also actinium. And moreover, thorium, which is kept at the second element in the actinides, doesn't have any electron in the f orbital. Then how are you putting in their block? The one who advocates for not bringing lanthanum and actinium down, they are kept mum. So this tussle is going on. So most of the people, they have brought lanthanum and actinium, and some guys have already suggested that lutetium and lawrencium to be kept here because they have their electron in the D1. So this should be, they are starting from in Odisha, we have a famous saying: if there will be two persons quarreling with each other, fighting with each other, then the third person will be the beneficiary. And I'm telling you in Odia, if someone is watching non-Odia or a native English speaker, speaking country person, that means in Odia we say, Dui jananka kadire, trutiyo jananka labha. If two people will quarrel, then the third person will take the benefit. So third party is saying that let us keep lutetium and lawrencium here in place of lanthanum and actinium, and bring lanthanum actinium, okay, here. So there are 14 lanthanides from lanthanum to ytterbium, and actinium to nobelium. So why? Because the F is complete and they have D electrons here. So you keep it as a D block elements. But nowadays the new research is trying to confirm that in lawrencium, the last element is not in the D. It is in the P, like nihonium 7p1. Can you believe it? If that will be proved, 50% proof they have got. And if they prove, then these guys who are saying lutetium and lawrencium, let us put it here. This will be D1 and this is 5D1, this is 6D1. But it is actually 7P1. How to keep there? So for everything said and done, we will be keeping lanthanum and actinium down here and say there are 15 lanthanides and 15 actinides. So now let me see what I left out. We have done everything. You have a look, I'll give you. Yeah. Yeah. Purely synthetic elements, I told you that after 95. Purely synthetic. I'm showing you, you can have your look, your periodic table which you have created. Yes. From purely synthetic, from americium. Americium, curium, berkelium, californium. All these can be prepared in bulk, some sizable quantity. I said up to californium, some sizable quantity has been prepared to keep it as a target for heating. But purely synthetic is from, americium. Neptunium, plutonium, they are available. Maybe trace quantity, they are also synthesized. Therefore, I have written purely synthetic is americium, curium, berkelium, californium. This is for formium. This californium, einsteinium, sorry. Yes, einsteinium, formium, mendeleevium, nobelium, lawrencium, rutherfordium, dubnium. All these up to organization, they are purely synthetic. And the elements which are natural as well as synthetic because of their scarcity, we are now synthesizing are technetium, promethium, these two, and polonium, astatine, which are almost extinct. Radon, we are not synthesizing. They are being produced naturally. Everywhere you find radon, pollution is occurring. We are not doing. Then francium, yes, we are synthesizing. Radium, sometimes we don't need radium, enough is there in the uranium and thorium ores. Actinium we are doing, and thorium we are not doing. Thorium is abundant. Its half-life period is of the order of 10 to the power 10 years, more than uranium. Yes, protactinium we are synthesizing. Uranium we are not synthesizing. Yes, neptunium and plutonium. That I have written it here. The elements which are natural as well as synthetic are this one. Technetium, promethium, polonium, astatine, not radon, francium, radium I have put an underline. Mostly they are not doing. Because it is available, not as much required for the research purpose. Nowadays nobody is using radium in the watches because they are harmful. They are used in some other purposes. Actinium, protactinium, neptunium, plutonium. Radioactive elements, I have already told my verdict. 94 elements. Sorry, this is a new file up to plutonium. Oh, radioactive elements is above 83 up to 94. Plutonium, natural. This is other file. I'm using an old file. So polonium onwards up to plutonium, they are naturally radioactive. Synthetic is from americium onwards. This is a new, old file I'm using, that is 94, this is 95. Technetium and promethium now synthetic. Some lighter, I told you that potassium 14, carbon 14, they are naturally occurring. And also calcium, whatever calcium we are taking in, is containing a little quantity of calcium 48. So, these are there. They are also beta emitters. Do you know bismuth 209, which was held to be stable, and I continue to say that bismuth is stable. After that, radioactivity starts. But nowadays, scientists are saying bismuth 209 is also radioactive. But the half-life period is 10 to the power 19 years. Earth is 13.7 billion years. 10 to the power 9. This is 10 to the power 19. So it is almost a stable element, but they are finding evidences that it will slowly and steadily disintegrate. But we will take it as stable. So we have done everything, and then I will tell you what happened. That Moseley, he was doing some X-ray experiment. X-ray spectrometer, X-ray, uh, you know, X-ray is an electromagnetic radiation, just like gamma rays, just like light, just like UV. X-rays is also electromagnetic radiation, no mass. But Röntgen, as we sometimes call Röntgen, discovered the X-rays. How X-rays are produced? That when electron beam from a cathode discharged lamp, they hit on a metal, then you know what happens? It knocks out one electron from the K cell, the first cell, takes it out. The electron, supposing one electron takes another electron, two electron goes out, and there is a vacancy in the K cell. Immediately that vacancy is filled by the jumping of another electron from the previous cell, L cell, to the K cell. During this transition, an energy photon, X-ray photon is produced. By that, X-rays are produced, and he did a lot of experiment to find a pattern, and he said that he conclusively proved that atomic nuclear charge, which you are saying atomic number, that is called the nuclear charge, the number of protons, is the basis of periodicity. So he changed the periodic law that the physical and chemical properties are periodic function of their atomic numbers. I'm not going to the details how he discovered atomic number, but one thing I will tell you, then you will tell me who is the real hero. At the age of 27, after discovering atomic number, nobody knew that the number of protons present inside the nucleus is the atomic number, and that is the basis of periodicity. The atomic number, they were calling serial number as 1, 2, 3, 4, 5. Then a place was vacant, then leave it, then the next number. So, but that is actually the proton number present in the nucleus. He proved it from his X-ray studies. Moseley. And the next year, he volunteered himself as a soldier in World War I. In 1915, in 1913, I am showing you how here, Henry Moseley, it is in fact Brooke, he proposed. It was his hypothesis that no, atomic mass is not the basis of the periodicity. It is atomic number, the nuclear charge. But he didn't have any proof. But the proof came from Henry Moseley, who took the X-ray spectra, and I'm not going to tell, because if you are a class 11 student, you must have known by now. He proved it and then propounded modern periodic law, and he found there are 4 places vacant. And after his death, all these elements were discovered. 43 was technetium. Technetium was not invented or discovered before 1913. Then this is promethium. This is hafnium, 72. This is uranium, 75. They were discovered after 1913. He found places. And then in 1915, he chose to join war, World War I. And he was killed at the age of 27 in the Turkey. And it is Berry who proposed the name of transition, because the electrons are entering into D. Therefore, the first concept of having long form of periodic table, separating the D series from the S and P, not keeping copper, silver in along with lithium, potassium, sodium, separating, because they have their D electrons at that time the electronic configuration was known came from S.D. Deming. But the ultimate hero was the Glenn T. Seaborg, University of Berkeley, California. He proposed the long form. In his time, there were many elements which were not discovered up to this plutonium. Then americium, curium, berkelium, and so on, which have been, up to californium in the bulk state, and then 5 atoms, 10 atoms, microgram. All these up to organation has been created. Now, these are the scientists, the latest after World War II. These are the scientists who are responsible for creating many synthetic elements, and will be knowing now. They are claiming within few years they will be synthesizing, creating the new element 119. And previously, when before 5-10 years, we were naming in a Latin style, supposing 112, now copernicium, we were saying, because there was a fight between these three groups. The Dubna Rasa group was trying to give the name with some Russian connection. The American, they were claiming to give the name with American connection. So also the Darmstadt, Germany, Darmstadt, there was a place where nuclear research was going on. They were particular about Germany. So the fighting was going on. IUPAC was always saying that you sit between yourselves, finalize who will be prioritizing, then you tell us. So ultimately, at that time, we were saying 112 was un by yam. One is called un. Another one is un. Two is by. And last is Un biam was 112, now copernicium. Now, 114, which is now flerovium, was called un quadrium. Moscovium was un pentium. Septium, Tennessine was 1 septium, and then organization was un octium. Now 119 will be created. They have failed. They will be successful after some time. This is ennium. Un 9 was called N and eum. Ennium. And then they will also synthesize 121 by nil. 0 is nil. 1 by nilium. So these were the Latin names which were given until and unless there is a consensus between the three groups, fighting groups. So we come to the end. I have already told that Mendeleev, he died at the age of 72, and when he died in 1907, where many elements were not, he was 72, and the other hero died at age of 27 during the war, World War I, and the other one, piles or some fistula surgery at home, and he died of very common influenza, where the doctor could not save him. And during his deathbed, he said to the doctor, "Doctor, you have science, I have faith." Now, a scientist is saying to another scientist, doctor is a scientist, "Doctor, you have science, I have faith." This statement speaks volumes of his, surrender to the divine. He was a spiritual person. Mostly died at the age of 27 in World War I. So guys, we complete our today's program. This session. And when we go to the second session at 6:30 to study the periodic properties, then you will be knowing how the changes are occurring. They're trained. But there will be a prize question for you. Who can answer? Tell me, which is the lowest boiling element in the entire periodic table. There will be some, you will be given cup. Those who have already got this cup, very beautiful cup, which you will be holding, will be keeping on your study table till your 12th pass out. It will be giving all information: atomic mass, name, everything, atomic number, everything. You'll be keeping it. Don't use it by drinking tea. It will be disfigured. You can do that when you are out of 12th class, you don't have a sibling, then you can ask your mom to use it. Yes. Yes. Who will say that which is the lowest boiling element in the entire periodic table? I'm showing you the periodic table that we created. We created a periodic table. Remember, we means you and me together. Yes. Now I allow Sibdat to unmute and answer.
Sir, helium.
Precisely helium. Are you taking the help of AI or internet, Google? If so, then this is a disgrace. That your heart knows better than me. If you are today, we are so fortunate that in our fingertip we can know anything and everything. So if you're doing so, then it is really very, very pathetic. If not, then definitely it is helium. Liquid helium has a boiling point of minus 268.9, or in Kelvin 4.22. The liquid helium is used in all the MRI, in spectroscopy, to provide a low temperature environment for the magnets, electromagnets, for the permanent magnets. Can you tell me how neutron was discovered by Chadwick? I will tell you tomorrow. That the trick is, one element, natural element, was kept as a target, and another particle was fired onto it with high speed. And then on the other side, some neutral particle came out, and whose mass was determined and was found to be almost same as that of proton, but having no charge. That was told as neutron. Anybody who can tell me how neutron was discovered? Yes, Sibdat? Hmm. Sibdat? No. Okay, I'm telling you how it was discovered. It was discovered in 1930 or 33 by Chadwick. He took, everybody knew from the atomic mass data, everybody knew that it looks so heavy, the atomy is so heavy, but the nuclear charge number of protons is so low that there must be some neutral particles, but they were not getting any proof. So the proof first came by Chadwick. He fired alpha particle from a alpha source. From some alpha source, a uranium 238. I will tell you tomorrow. There are alpha, beta, all these sorts. So he took one alpha source and he fired these alpha particles on beryllium 9. The natural isotope of beryllium is 9. And when he hit, this is the projectile and this is the target. When it hit, Then he found on the other side some neutral particle coming out, and you can do the arithmetic. 4 plus 2, 6. So this is 0. So 6 will be here. 9 plus 4, 12. So minus 1, then it will be 12. So the result was carbon. Beryllium was a gray, silver gray metal. It turned into black. This is the transformation. We call it nuclear transmutation. Transformation. This is the projectile, and this is the target. This is the projectile, and this is the ejected particle, and this is the product. So in this way, neutron was discovered. Can you tell me how many isotopes are there for oxygen? Oxygen. Yeah, Alisa, you are my Indian granddaughter. I will not tell in that short name. It is a public discourse that we are having. But yes, you are my Indian granddaughter, Alisa Panigrahi from Berhampur. Welcome. So, who can tell me how many isotopes are there for oxygen, and what is their relative abundance ratio, and which one of them is radioactive? Okay, I will give this to Anisha because I congratulate three of you. Siv is missing out. Maybe some net problem, doesn't matter. Anisha, you open. I have already. Anisha, can you open? Can you open? Ani, open. Yes.
3.
3. What are those? What are the mass numbers?
6, oxygen 16, 17 and 18.
Yes, precisely. And what is their ratio? It is, these two are almost negligible. Now, this is 99.78. This is 0.02%, and 18 is 0.2%. So I think, yes. So the next question to you, what will be the average atomic mass of oxygen that we use for our calculation? Any answer from the YouTube viewers who are watching? If there are 3 isotopes, and there are 2 isotopes per chlorine, 35 and 37, and the average was 35.5. So in this case, what will be the average atomic mass? Oh, well, Sarthak?
Sir, approx 16.
Yeah, precisely, Sarthak is correct. Approximately 16. Because when you find out the weighted average, this is 99.78 into 16. Actually, it is not 16, it is 15.999 something. But the mass number is 16. But this is atomic mass that we are, sorry, isotopic mass we are supposed to use. But 15.997 is not different from 16. So we take 16 plus 0.02 into 17 plus 0.2 into 18 by 100. So it will be coming close to 16. If the other isotopes are available in a very minute quantity, the most abundant isotope is present in more than 90%, then the average will be close to the isotopic mass of the most abundant isotope. And interestingly, this 0.2% oxygen, tomorrow we shall see, is necessary as a projectile to prepare many synthetic elements. Not, and sometimes O16 is required. But see, we have to separate we have to separate the 3 isotopes, and we need pure 18 isotope and fire onto a target and get another new element. So we are almost can anyone tell me what is the use of which you have seen in the song? Try to watch the video again and again. And let me, before I close this formality, I have to maintain that you share this video, not this video alone, but the song video, which is very important, because that song is the pivot, the central theme of our celebration. More and more people should watch it and try to appreciate it. If they don't like it, let them not. Don't worry, we can't impose. But if they like, they should also share. So my request, I urge upon you that whoever is watching this video should share this video as well as the song video separately to all your group members who are students and teachers, anybody. And if you have not yet subscribed to my channel, SST Chemistry, please consider to subscribe. If you have already done, then thank you very much. Because I'll be producing more and more interesting videos, not as lengthy as today, shorter videos, which you will be benefited. So tell me the last question, what is the use of titanium and zirconium? Titanium and zirconium fall in the same group, that is group 4, transition series titanium and zirconium. First titanium, then zirconium. Yes, Arthak. Titanium.
Sir, titanium and zirconium are used for
No, your titanium aircraft. You know, Jasmine, you know, many guys, they take a shortcut route. Shortcut route is aircraft parts. Titanium alloys are used in some aircraft parts. But I told you what is the latest use of titanium. Titanium is used for dental implant. If your grandparents or your parents have ever have an implant which will not be, removed, an implant. I have an implant. The first they will pierce, they will drill, and they will put a titanium implant. Simply a metallic implant. Then the cover which looks like a teeth is actually not the titanium. It is, it is piercing through the jawbone and it is going down. And then crown. These what you see, they are crowns and they are made up of zirconium. So one brother, and see, the frame that I am using here in my glass spec is pure titanium. It's so lightweight, so cozy, and so easy to handle, so light, so strong. And you don't find that I'm using a glass as if I'm not using anything. So, and it is very, very durable. So that here is one example of titanium and a tooth implant, and then zirconium is used as a crown, as a dental crown. So with this, you take some rest. I congratulate particularly those who repeated today. I requested them to repeat because this is an odd time that I had this program, but I had to do that. There was no way out. But it spilled over to the tomorrow morning 7. So Anisha, Sarthak, and you tell Mr. Shiv to definitely join tomorrow at 7 a.m. morning. Bye-bye. Thank you for watching. And put a thumbs up if you like the video. And don't hesitate to subscribe if not. Bye. See you in the evening with my colleague, Dr. B.N. Das at 6:30. Be ready. Bye-bye. Bye. Bye. Anissa, Sarthak, bye.